Bismillahirrahmanirrahim. Assalamualaikum and good day everyone. Alhamdulillah. We are now going to proceed to chapter 6, circular motion and other application of Newton's law. We are now extending the particle in uniform circular motion model, whereby here we want to learn about the centripetal movement, okay, or centripetal acceleration. So if you see here, this object is moving in a circular path. Okay, so we know that this object going to experience a net force that causing the object remaining within the circular path. Okay, so this force, okay, is directed toward the center of the circle, which is the one going to keep the part moving in its circular path. Okay, and the force is actually always pointing to the center of the circle. And we are going to symbol this force F R, okay, where R is symbolized for the radius of the circle. Right, so always to the center, okay, regardless which position of the part or object is, it's always to the center of the circle. Right, based on Newton's second law, the net force acting on an object is equivalent to MA. So for this case, it's AC. Okay, what does that mean by AC? It's centripetal acceleration. Okay, so and we know that the centripetal acceleration is V square over R. Okay, this is tangential speed over the radius of the circle. Okay, now, okay, when the string breaks, the part move in the direction tangent to the circle. This is a proof of the V, the tangential velocity or speed just now. Okay, it must be tangent to the position or the line of the part, right? And from that, we know that, okay, just now, F equivalent to MAC and AC is equivalent to V square over R. And the direction of the V, okay, is tangent to the position of the object. And the direction of the AC always according to the direction of the FC or simply F. So the same direction, right? Because it's a vector. So this direction is according to this, okay, or vice versa, right? Example 6.1. Okay, a small ball of mass M is suspended from a string of length L, right? The ball revolves with constant speed V in a horizontal circle of radius R, as shown in this figure. Okay, because the string sweeps out the surface of a cone, the system is known as conical pendulum. A special name for this kind of system, we call it conical pendulum. Not simple pendulum, but conical pendulum. Find an expression for V in terms of the length of the string and the angle it makes with the vertical in the figure. So, before we proceed, we list down all the forces acting on this object, where we have weight downward. How we know the weight is downward and within this direction? We have to bear in mind weight always to the center of the earth, right? And here we have tension. To the respect of this object, the tension must be away from it. So this is the direction of the tension. And at any position within the circular path, the object making R, okay, as the radius of the circle to the center. And okay, this L is making angle of theta to the straight line here. So from this diagram, we are now going to convert it into free body diagram. Okay, of the object. Okay, where we list down all the forces acting on it and we resolve the T into Y component and X component. We can prove that this angle is actually the same angle to this. Okay, mathematically. So we have the components of the t. For the y component, it's t cos theta. And for the x component, it's t sin theta. Now, we're going to proceed with the Newton's second law. Summation of Fy equivalent to MAY, originally. Okay, but we know that the object is moving in x direction. So, the AY is 0. Right, so what we have along y-axis is t cos theta, positive because it's pointing upward. As usual, this is our setting of reference axis. Then we have mg downward. Okay, that is why it takes negative sign equivalent to 0. So from here, we have t cos theta equivalent to mg. For the x component, okay, we have summation of fx equivalent to MAC. How we know this is AC? Because it's moving in circle. So all the time, okay, AC is to the center of the circle. We have t sin theta, right, as the x component force. Okay, what else? No more, right? This is the only force along x, which is equivalent to the MAX, and happen to be our AX is the AC. Then we may substitute the AC with V squared over R. From that, okay, now we may simultaneously solve the first and the second equation. Okay, if we see here, okay, we may do sine theta over cos theta is equivalent to tangent theta. We make a ratio. Okay, this is equation 1. And here we have equation 2. Okay, so equation 2 over equation 1, which gives us t sin theta, okay, over t cos theta equivalent to m v squared over r. This is for equation 2, right? Over equation 1, which is mg. So the m here can be cancelled out. The t here can be cancelled out. And sin theta over cos theta is equivalent to tangent theta. That is why we are left with this. Tangent theta equivalent to v squared over rg. Okay, from here, if we are interested in the velocity of speed, tangential velocity of speed, then we may arrange this equation into this. V equivalent to square root of rg tangent theta. If we want to substitute the r, okay, with the information from L, the length of the pendulum, okay, we may put as L sin theta for the r, okay? Because you have this triangle, right? Based on this triangle. Okay, you have theta here, you have r here, you have L here. Okay, so you may have r as L sin theta. With that, you substitute the value of the r with L. L sin theta. So you will have finally this equation. Right. Example 6.2, how fast can it spin? Okay, a part of 0.5 kilogram is attached to the end of a cord, okay, 1.5 meter long. The part moves in a horizontal circle as shown in the figure. If the cord can withstand a maximum tension of 50 Newton, this is maximum tension that the cord may withstand. Bigger than this, it will break. Okay, what is the maximum speed at which the part can move before the cord breaks? Assume the strings remains horizontal during the motion. So again, the part is taking direction, okay, clockwise direction within a circular path. So the F exists within the cord, which is we know is the tension in the cord. Also is the centripetal force, okay, FC or FR, okay, which is always to the center of the circle. The direction of the AC is according to the direction of the FR. From sum of F equivalent to MA, C, the F that involved, okay, regardless which position, okay, let's say madam take this position, right? So you have FR to this direction, AC also into this direction. So sum of F is equivalent to MAC. So the F that we have is the T, okay, M, then the AC is V square over R. Right, that is how we have this equation. From here, rearrange for the V is square root of TR over M. Okay, to have a maximum speed, it's directly proportional to the square root of T. Okay, it's the T also must be the maximum value, which is already given to us 50 Newton. So from here, we know that the speed maximum is 12.2, right, meter per second. So it cannot exceed this amount. If it exceeds this amount, this is also going to exceed. Therefore, it will break. Okay. Suppose the park move in a circle of larger radius at the same speed, v. Is the cord more likely or less likely to break? Okay, just now we have in our hand the equation of T. T is equivalent to M V square over R. Okay, so if the V is, the R is larger, the V maintain the same, okay, remain the same, the R is larger, okay, is inversely proportional to the T, right? So if the R is larger, and then the T will be smaller, right? That is why it's less likely to break. V remain the same, R is larger, okay? So what will happen to the T? T will be less, okay? So less amount of T, less than maximum value, then less likely it will break. Okay, because T is inversely proportional to the R. Example 6.3. What is the maximum speed of the car? A 1,500 kilogram car moving on a flat horizontal road negotiates a curve as shown in the overhead view in the figure. If the radius of the curve is 35 meter and the coefficient of static friction between the tires and dry pavement is 0.523, find the maximum speed the car can have and still make turn successfully. So as we know, okay, this is a top view, okay, overhead view. So the force that maintaining the car, okay, within a circular path, okay, is the static force, okay, static frictional force between the tires and the pavement or the road, right? So how is it happen? So you just imagine if this is the tire, okay, how the tire going to move? This is the road, okay, the area within the contact area between the tires and the pavement or road going to be held statically by frictional force. That is the one causing the other part of the tire going to move. Okay, that is how overall, okay, the car going to move to the right. It's because of the tire is rotating. Get it? Okay, so the frictional force exists between the tire and the pavement of the road is actually static frictional force, right? So since the car is in circular motion, okay, circular path taken, so the static friction is into the, always towards the center of the circle. Right, so this is the back view of the car. Now we're going to see normal force and also weight. Just now, from here is top view. We cannot see the normal and the weight, right? So we have normal upward, weight downward, and static frictional force to the left. Okay, so from here, okay, we are going to do summation of Fy is equivalent to 0. Why is it 0? Because as usual, this is our setting of reference axis. Right, so we have here, okay, normal, okay, plus negative of mg equivalent to 0. Why is it 0? Because there is no movement along y. From here, normal is equivalent to mg, right? And we always know that Fs maximum is equivalent to mu s n, okay? And our Fs here is the centripetal force, because it is the only one that keep the car, okay, moving in a circular path. Or this is the only net force along x. If you want to put it even in a bit clearer, okay, we put it like this. Okay, and fx here we have negative fs, okay, and ac is also negative direction. Y is also to this direction. AC always the same direction to the FC. Okay. Okay, now we already have this idea. Okay. From now we have, just now we have Fs max must be mu s n, okay, and Fs max here is also Fc max. Okay, so mu Sn equivalent to m AC max. Okay, what is our AC max? Is V max square over R. Okay, and our N mu S mg. Right, so from there we may cancel out the m simply, okay, and to have V max we going to rearrange the equation from here, okay, or you may do it like this, and finally we will have, okay, V max equivalent to square root mu s g times r. If you substitute all the values, you will get V max u equivalent to 13.4 meter per second. Suppose a car travels in this curve on a wet day and begins to skid on the curve when it is its speed reach only 8 meter per second. What can we say about the coefficient of static friction in this case? So just now, right, we have V max equivalent to square root mu s gr. Okay, So if now our interest in or static coefficient of static friction, then we rearrange this equation, make mu s as our interest. So from here we'll see it's equivalent to V max square over GR. Okay, so if we substitute all the values given, okay, you will get 0.187. Okay, what can we conclude? This is actually less than, isn't it? Because the original one is 0.523 and here we have only 0.187. So because of the wet condition, okay, then the mu is reduced. Right. Example 6.5, riding the Ferris wheel. A child of mass m rides on a Ferris wheel as shown in the figure. The child moves in a vertical circle of the radius 10 meter at a constant speed of 3 meter per second. Okay, A, determine the force exerted by the seat on the child at the bottom of the ride. Okay, express your answer in terms of weight of the child, mg. So, this is a free body diagram of the child. Okay, we have normal. Okay, at the bottom, this is the pattern of the normal. Okay, always normal to the contact surface, and weight is downward. So from here, okay, summation of F, okay, along Y is equivalent to MAC. Why is it? Because, okay, this is the circle. Okay, here is the child. So normal is here, weight is here. Right? So if you see here, this is also direction of the AC. So we have, okay, summation of Fy equivalent to MAC, and what Fy we have? Normal minus Mg equivalent to MAC. So this is AC. Right? So from this, normal at the bottom is equivalent to mv squared over r plus mg. Okay, we may simplify the equation. Okay, put the mg outside because the question asks for it. Okay, so mg parenthesis 1 plus v squared over rg. Right. So now we are going to substitute the value of the v, the r, and also the g. So you will see, okay, the normal at the bottom, okay, will be 1.09 times of the mg of the child. Okay, B, determine the force exerted by the seat on the child on the top of the ride. When it is on the top of the ride, okay, this is a child, the seat of the child. We have normal on top position. We have weight. Okay, we have AC in this direction. Okay, then summation of F, okay, again along Y is equivalent to MAC. Okay, but we have here mg is taken as positive, okay, which is similar to the AC. It's downward, sort of we are having our setting like this, positive y. Okay, mg minus normal at the top equivalent to MAC. This is AC. Okay, so from here, okay, we may rearrange the equation. You also may use this actually. The same setup as usual, okay? So you are taking positive 1 upward to the right as positive x. So what will happen to this equation is you are going to have normal at the top, positive, okay, minus mg, okay, equivalent to m, okay, negative v squared over r, okay, because your AC is downward, so it has negative sign. Okay, so okay, if you multiply this equation with negative 1, then you are going to have mg minus normal at the top equivalent to mv squared over r. It's the same thing. Okay, then rearrange, okay, put the normal as our interest, you will have this equation. So if you see here, it's minus, right? What does that mean? Less, isn't it? Okay, so you see here, if we substitute the value, the normal experienced by the child at the top position is 0.908 times with the mg of the child. Okay, will be less. It means less. Okay, compared to the bottom position. Okay, so it will be the child will experience like less weight, okay, at the top position. Okay, at the bottom, more weight or heavier. Okay, suppose a defect in the Ferris wheel mechanism causes the speed of the child to increase to 10 meters per second. What does the child experience at the top of the ride in the case? So, if we substitute, okay, the value of 10 meters per second to the equation for the normal at the top, okay, we will get the value of normal at the top negative 0.020 times mg. So what does that mean? This is impossible. Okay, means that the child going to loses the contact with the seat. Okay, fly away, thrown away. Okay, accident happen. That is the meaning of this value. Alright, that's all from me for this chapter. Thank you very much. Do not hesitate to ask questions if you have anything not clear on this lecture. Thank you. Assalamualaikum.